Now, the filter, what we're saying is that any permutation of the columns of that filter is equivalent. So what we have is, if we take a permutation matrix, which we call P, yeah, and if we can make that, so we can imagine the set of values of W such that W is equal to some times a permutation matrix for all the permutation matrices. This set is what we call an orbit. And so if you're thinking about it as numbers on the number plane, then you've got your sort of, it's a symmetry set. So you could have the symmetry sets of that. I'm just drawing this slightly random. This is not necessarily the exact symmetry set, but there's a symmetry set. And so you just label any one of these elements as W0, and then you have all your different symmetry points, and you're saying all of those points are actually equivalent and they make one orbit. So what we now say is that this set here, which we'll call W like that, yeah, that's an orbit. This set itself is a element of what's called a quotient space, and our quotient space is, in our case, is C M cross N into the symmetry set for n dimensions. So now what we want to do is, what can we make a distance between W and another orbit, W dashed? And we want to make a distance between these two orbits which satisfies our triangular inequality as over here, but now on this. And so this will be a valid distance measurement that takes into account the ambiguity of permutations of our solution. The nice thing about this, because these are sets, you can use a measure called the Hausdorff, might spell it wrong here, Dorf distance. And the Hausdorff distance, under certain situations, gives us a measure which is the distance between two sets. You take your particular orbit, okay, like here, which I've done here, or the distance between a set, and you might have another point, which I'll put on like that, and that we want to know how to measure this distance between sets. And what the Hausdorff distance says, you grow each of the points in one of your sets by a certain amount. We can say W delta is W grown by a distance delta, and we can define that distance with any valid distance metric, and the obvious one to do is the Mahalanobis distance that we defined over here. Then we find the smallest delta such that W delta is a superset of the other point. So we grow these points by enough so that they encompass all of the other points in the other set. The full definition of the Hausdorff distance is that we also find the smallest delta dashed such that W dashed delta is a superset of W. So the distance between the two sets is equal to the infimum, or if you really want to be absolutely specific, of the delta and the delta dashed as defined there. So hopefully what we've done here is show how we can use the Hausdorff distance and the Mahalanobis distance to define a distance measure between our orbits, which represent the solutions of two algorithms have got to, and so we can compare these two filters and say, are they actually getting closer up to the permutation ambiguity that is naturally inherent in these types of equations. And then that allows us to do a variety of different things. It asks us to say, you know, are two different algorithms actually converging on the same solution? Or also in debugging, it allows us to ask the question of, you know, is there a bug and is it going wildly, are we getting massive errors because it's not converging on something that looks like the right solution? So yeah, so that's the Hausdorff distance. So we have the initial definition of the problem, we have the definition of a distance metric, we have a definition of the Mahalanobis distance, we then have the definition of orbits and quotient spaces, which is the framework which allows us to define the Hausdorff distance, which then allows us to define this valid distance metric on the space of demixing filters for blind source separation. Well, normally, if I wasn't doing a video, I'd at this point say any questions, but